Hello and welcome to lesson 11 of this Introduction to Probability of Wolfram U. The topic for this lesson is simulation and estimation. Let's begin. You now understand random variables well theoretically, but to get a useful understanding of randomness, simulating a random variable as data is often useful. Conversely, it's often also useful to model some random data as a probability distribution. The transition from data to model and from model to data is essential in data science. In this lesson, you'll learn how to simulate data, estimate distributions, and quantify your certainty. Starting off with simulation. To simulate data from a distribution, just use the random variate function for a list of n samples from the distribution. For example, let's simulate a die. That would be the probability distribution of the probability 1 over 6 for the values 1 to 6. Now, simulate some data with random variate over the distribution of the die with 100 variates. That is an example of that distribution. You can imagine rolling the die 100 times and getting these results. To visualize a bit, let's plot it in a histogram with the simulated data as a PDF to get the probability and not the frequency. Next to it, let's plot the theoretical PDF with a discrete plot of the PDF over the domain. The theory overall agrees with the sample, as probabilities are close. This is standard to visualize data against estimates too, so be familiar with this. Okay, so we did it with a discrete random variable, but what about the continuous version? Imagine a region with annual tornadoes, where the time until the next tornado is a random variable with PDF e power minus x. Just create a distribution with e power minus x and simulate 100 variates over that distribution. This is what continuous random data looks like. As seen before, use the histogram of the simulated data and plot the theoretical distribution to confirm the matching. Now, what about modeling the distribution from data? The estimated distribution function estimates the parametric distribution from data. In other words, it can estimate a complete PDF from a PDF with unknowns in it. For example, let's say you have all your classmates' GPA scores in this list, and you know GPA distributions usually follow a PDF 2x divided by a squared. Estimate with the data and the incomplete PDF, and you get the estimated distribution. Compare the histogram of data to the estimated distribution, and you see a similar trend. Let's do this for another example. You have the ages of retirement home residents when they arrived. And you know the PDF should be 4x cubed divided by 15a power 4, where x is between a and 2a. So write the distribution as a function of a, then estimate the distribution, and as usual, plot the data against the distribution for confirmation. With estimated distribution, you get an estimated distribution back. But what about the parameters? What value of a did the algorithm choose for the past example? To get the parameter values, use the find distribution parameters function. If you just apply it on the data given and the age distribution, you get each parameter and their estimated value. If you just write the distribution and replace the parameters by their estimated value, you get back the estimated distribution. What if you don't even know what the PDF should look like? You only have data. Then use the find distribution function. It fits the best and distributions corresponding to your data. For example, if you just load the data set on the age of patients affected by melanoma and find its distribution, you see it's a normal distribution, and you can compare the data to the estimated distribution. Remember these three steps: load, estimate, plot. This time, it's the time to kidney infection. Load the data, estimate the distribution exclusively on the data, then plot the data and the distribution to confirm the trend. Okay, if you go see your boss and explain that the trend just looks right, your advice is unlikely to be trusted. To quantify how close your model is to the actual data, you need some kind of hypothesis testing. The most appropriate here would be the distribution fit test, which gives you the p-value for your data against the distribution. What's a p-value? It's a fitness measure where 0 means the distribution does not fit the data and 1 means it fits the data perfectly. Let's say you have a distribution with PDF 6x times 1 minus x and the corresponding data. If you plot it with data and model, you see it fits very closely to the curve. And if you compute the fitness of the data against the distribution, you see a high fitness value. In practice, depending on the application, a p-value greater than 0.2 or 0.3 may be considered significant. Of course, the Wolfram language also has more tools for hypothesis testing, such as location test for testing similarity between means, the variance test to test similar variances, and location equivalent test to test the mean of multiple datasets at the same time. If you need more information, see this guide on hypothesis testing. To summarize, the transition from data to model and model to data is essential. To simulate data, simple, just use random variates. To estimate distribution, use estimated distribution, fine distribution, or fine distribution parameters, depending on what you want. Remember, load, estimate, plot to verify. If plotting is not enough and you need to quantify your estimation, use the distribution fit test. Fine distribution can often be inappropriate in applications, and estimated distribution is almost always preferable, assuming you know what kind of distribution you're dealing with. But how do you know what kind of distribution to use? To build up that knowledge, the next two chapters focus on the study of popular parameterized distributions.